So, proofs are a huge part of university. There's actually whole courses you take just on proofs, geometric proofs, calculus proofs, geometry. It's a big part of engineering. If you're going to go through any of the sciences, you're going to have to take courses that you're going to be doing proofs. And I guess it's kind of good because you always know the answer before you start. But sometimes they take you up to a page, 2 pages to show how you get from that side to that side. So the more, I guess, tools you have and the more kind of stuff you know as you do a proof, the more you're able to kind of chop it down till you get the left side looking like the right side. Now, we did these in 30-1 already last semester, and some of you guys are going to be doing them again here. But I just want to talk about the main ones right now that you're going to see a lot. First of all, this one here, sine squared plus cos squared equals 1. That is your Pythagorean identity. And that works really well with the unit circle, because the unit circle, a squared plus b squared equals 1, right? And, or x squared plus y squared, x is cos, and y is sine. I guess I shouldn't miss these ones. You guys, we did these already, but these are your reciprocal ones. And tan is sine over cos, and cotan is cos over sine. Okay? Now, also be aware that you can just, by, say, subtracting sine squared x to both sides, get cos squared theta equals 1 minus sine squared theta. So you have to be able to recognize those too. And these all come with practice. The more you practice these and you see 1 minus sine squared theta, you just know that's cos squared theta. And the closer you can get to getting rid of, in that case, 2 terms down to 1, makes your life easier. Now, if you go and divide everything by cos, okay, you're going to get this formula here, which is tan squared theta minus 1 equals secant squared theta. And if you take the Pythagorean identity and divide it by sine, you get this one. Now, the best part of proving identities is don't prove both sides at the same time, okay? Just move one side, because what happens if you keep working down both sides, they never look like each other, right? They can miss each other. So keep one still. When I was a camp counselor, that was the big thing. When you got lost, stay where you are, okay? Because if we're looking for you and you're looking for us, we'll never find you, okay? So it said hug a tree, okay? Just stay there. Stay by the tree. We'll find you, okay? It's easier, but if 2 people are moving, you never find them. So if you are moving the left side and the right side, sometimes you'll never find each other. Just move one side. I always move the more difficult side. So here's some kind of tips that I'm sure that you saw if you're in 30-1 is move from the more complex to the simple. Okay, so the more complex sign, get rid of, so in terms of sine, so basically get rid of tans. I find like these, they only have so many proofs, right? They only have so many of these, so they put tans in there, you get rid of them, all of a sudden things cancel like crazy after. Always look out for your Pythagorean identities, and make sure that you all functions with the same argument. Now, argument in these is the theta, okay, or make sure they're both theta, or they're both 2 theta. Not sine theta does not equal sine 2 theta, okay? So those are called the arguments or the angles. Okay, so let's just do a couple. Now, there are many, many different ways to do these. These, for me, probably these are the hardest to mark, because students, if they don't know what they're doing, they will, their last step, they will put equals, you know, left side equals right side, right? But then they do a bunch of like things that aren't even true, and then they start to make it look like it, and then they have that, right? So for me, it's really hard to go, where did they get that from? You know, so these are tougher to mark because there's so many ways to do it. Maybe you're going to leave the left side alone, and you're going to totally work down the right side. Maybe some people are going to do the right side, and then when they do the right side, they do it totally different than the person beside them. Okay, so let's work with the left side just for fun. Now, again, get rid of your tans. So on the left side, I have sine theta times sine theta over cos theta. And I just draw a line here. Okay? So right away, that gives me sine squared theta over cos theta. Okay? Now when I see a sine squared, and on this side I see a minus sign, this is telling me that this one is using the Pythagorean identity. So this is 1 minus cos squared theta over cos theta. Now, this step isn't really necessary, but I'm just going to do it because I don't want to lose anyone. So this is the same thing as 1 over cos theta minus cos squared theta over cos theta. So 1 over cos squared theta is secant theta. And we're going to cancel one of these and one of those, so that's cos theta. And then I can say left side equals right side. That makes sense? Yep. Yep. Sort of. It's really one lesson. But there's 2 of them in it. Okay. Now, this one here, the way I've saw it done in notes is they simplified the right side. And I simplified the left side. I thought it was way less steps. But I saw that the cotan and the tan, and I'm like, okay, let's get rid of those. So this is the same thing as 1 plus. Now cotan is cos x over sine x times, now be careful here, that's a y, right? So sine y over cos y. Now another really common thing to do is when you have a number plus something else, right? We have to get that number together with it up top. And the only way you're going to do that is by doing a common denominator. So this will be sine x cos y over sine x cos y. See, that's 1. Plus, I have cos x sine y over sine x cos y. Okay, now this can be written as sine x cos y plus cos x sine y all over sine x cos y. Now, are you seeing this? Now, are you also seeing that this is an addition subtraction identity? So this is the same thing as sine x plus y. And that's over sine x cos y. Left side equals right side. Now some of you are probably thinking, I would have just went with this one, and then got this, right? And then worked through it that way, split it up, right? And then you would actually start going and looking like this, and then you'd get to there, okay? There's so many ways to do these. And is it wrong to work halfway down this one and then halfway down this one till it equals each other? No, it's not wrong to do that, okay? Students do usually struggle with that way a little bit harder, but sometimes, like I could have stopped here and then turned this one into this, all over sine x cos y, and then I would just say left side equal right side, okay? Okay, you guys had the assignment there? Okay, so the other 0.5 of the one lesson. Okay, so now let's just talk about single angle trig identities. Now here's a graph of sine x, and it says, well, when does sine x equal 0? Well, it equals 0 here, 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 and here. So since this is x is in the reals, it would take me forever to actually list all of the times that it equals 0. So I need to come up with a faster way to do that. So when does sine x equal 0? So sine x equals 0 when n pi, n is in the integers. So this is for infinite. Now b is very different. B gives us for a finite. And that's when cos x equals -1. Well, cos equals -1 down there and down there. So I would just say that x would equal -3 pi. Oh, sorry. Yeah, -3 pi and pi, negative pi. Okay. Now solving trig equations algebraically. If you have 2 sine theta plus 3 equals 0, and it wants you to solve it in 0 and 2 pi in that domain. Well, the first thing you want to do is get the ratio by itself. Sine, cos, tan, secant, cosecant, get it by itself. So the first thing I will do is I will minus √3 to both sides. So then I will get 2 sine x equals -√3. Then I'll divide by 2, and I get sine x equals -√3 over 2. Now, there is the long way to do these, and if you know your unit circle, you can just give the answers right now. Okay? Like, does anyone know when cos equals, or sorry, when sine equals -3 over 2? So, right here and right here. So when x equals 4 pi over 3 and 5 pi over 3. So the long way to do them, though, is to, first of all, isolate trig function. We just did. Now that you're going to have to do either way, but the second one is determine the quadrants. And I guess even if you were just using a unit circle, I think that's probably not a bad idea. And then this is where you can skip all of this, but the next is determine reference angle. And in this case, the reference angle would be, you take sine, and you're just going to do root 3 over 2. So you would get pi over 3 as your reference. Okay, and then you go, okay, we were in these two quadrants, so we're going to do pi over 3, pi over 3. Okay, and then you can, so that's, the next was to sketch reference, which we just did. And then find the solution using this, right? If it would have been quadrant 1, reference angle is that. If it's quadrant 2, pi minus the reference. 3 is pi plus the reference. 4 is 2 pi minus the reference. Now, if you're ever doing general solution is over a domain of the reals. So, in this case, this is for sine, right? So we would do, and cos. So you'd go 4 pi over 3 plus 2 pi n, because every time you go 2 pi, and then comma 5 pi over 3 plus 2 pi n, and then make sure you say n is in the integers. So this is general solution, if you're ever asked general solution. And just make sure that you remember for tan, it is n pi. N is in the integers, right? Tan repeats every pi, where sine and cos repeat every 2 pi. Okay, now this is the part I was talking about that I know caused you guys a little bit of grief last semester. And that was with multiple. So when cos x equals 0.5, well, that's just off your unit circle. But when it's cos 2x, cos 4x, cos 6x, remember those? No? Okay. So when cos x equals 0.5, well, that's here and here. So you go 0.5, right? And this would when it equals 0.5. And in this case, it would be at 60 degrees and 300 degrees. Now, if you're doing when cos 2x equals 0.5, and we're just covering this right now in 30, that's a horizontal stretch by a half. That means half all of these x values. So when you half everything, it squishes it. Okay? It's a horizontal stretch by a half. So these become your new answers. And not only do you want to half the old answers, so first of all, I know there's going to be 4 because there was 2 when I was doing cos x. There'll be twice as many when I do cos 2x. Okay? If it was cos 5x, there would be 10 answers. Okay? You just, whatever the number is, multiply it by the number of answers for cos x. Now, since I will half these, because I'm doing a horizontal stretch by a half, so that would give me 30 and 150 degrees. Now, what's the new period? How often does it repeat? Every 180 degrees. And that's done by 360 degrees over b. Period equals 360 over b, right? So that would be 360. B is 2, so that's how you get your 180 degrees. And all you do to the first one is you add 180, and you will get 210 degrees. In the second one, add 180, and you will get 330 degrees. That makes sense? Yeah. When students were showing me how they learned that one, I was like, okay. And you know what? This is how it's taught right here. And this is a really complicated way to do these. So it's almost like we have room to write, but I want you to cross this out, and in between we'll write the easier steps to do it, okay? Because this stuff doesn't really make sense. Where if you know about horizontal stretches, it should make sense. Okay? So, the first thing we're going to do is solve to isolate ratio. Okay? So, we're doing this one here. In the domain 0 to pi. Oops, not the ratio on the ratio. Okay, so the first thing I will do is I will subtract 5 to both sides, and then I'm going to divide by 10. So I will get tan 4x equals negative 1/2. Did I just write tan? What are we doing here? Sine 4x equals negative 1/2. Does that make sense? How we got that? Now, the second thing you do is solve for sine x equals negative 1/2. Okay, so I'm going to draw an arrow here, and I'm going to do it visually. Sine, so we get cast, right? So when is sine negative? It is negative in these two quadrants, right? And when does sine equal negative 1/2? There and there. So what would be my angles, just by looking at it? So when x equals, oh, sorry, we got to be in radians because it's a radian. 7 pi over 6 and 11 pi over 6. Okay, do you get up to here? Because this is the hard part. The rest is easy. Okay, so that's when sine x equals negative 1/2. Now, the third thing, if sine x has two answers, sine 4x would have how many answers? Would have 8 answers, yeah. This is my patented way to do these. And you can see the textbook or the workbook you guys use doesn't do it this way either, but this is the easy way to do it. Okay, so all I want you to do is put down 8 blanks. 1, 2, 3, 4, 6, 7, 8. Okay, you'll have 8 answers because we are doing a horizontal stretch by a quarter. We're going to squish it in. So you can kind of see this thing, right? It's been squished into this. Now, so if sine x equals 7 pi over 6 and 11 pi over 6, sine 4x would equal, so we will do a horizontal stretch by a quarter. right? We will multiply those two. Do you see how we multiplied these two by a half to get these? And that's how we would do it normally, right? That's how if I just gave you this picture and I said do a horizontal stretch by a half, I hope you would half all the x's. Okay? So we're going to half, well no, we're going to quarter these x. Okay? So then for sine 4x, what would be my first answer? 7 pi over 24 and 11 pi over 24. Does that make sense? Okay? And that's why I teach it this way. I think it makes sense, right? We've done horizontal stretches. So that's your first two answers, 7 pi over 4. And I'm going to do the other one in red because it'll make more sense. Oops, 24. That wouldn't make sense, would it? Okay. 24. Now, the way that you find this one, and this one is just add the new period. So that's kind of, 4 has two parts, A and then B. Find other answers by adding new period to each. And right from 30-1, the formula for period is 2 pi over b, right? B is, what's b? Right? When I say b, you guys know that I'm talking about this value right up there, right? So 2 pi over 4 makes this pi over 2. Now adding pi over 2 every time will get me all those other values. Because just like up here, okay, the period here is 360. Well, there isn't another one, but this one, right? You just take the new period to get the next one. Now, when you get pi over 2, it's really hard to add pi over 2 to 7 pi over 24 because it's not a common denominator. So to make it a common denominator, aka 12 pi over 24, right? And then I can add 12 pi over 24 to everybody. So I'm just going to write this here, 12 pi over 24, 12 pi over 24, 12 pi over 24. So I'm just going to work with 7 pi over 24 right now, plus 12 pi over 24 would give me 19 pi over 24. And then I'm going to add 12 pi to that one, gives me 31 pi over 24. And then I'll add 12 to that, and I will get 43 pi over 24. Okay, and then I'm going to do 11 pi over 24 to get all of these second ones. Because of my domain, there was 2 answers, and I will have 8 answers, and that's why I put my 8 blanks before I even started. Okay, and the other ones would be, so I would add 12, so that's 23 pi over 24, and then 35 pi over 24, and 47 pi over 24. Okay, now the general solution for this one, now you can kind of see this really, I don't know why I didn't notice this. I would have put this, it's 2 pi over b, really, right? If we can keep the same b as we used in 30-1. So this would be, my general would have been 7 pi over 24 plus pi over 2n, and 11 pi over 24 plus pi over 2n. N is in the integers. Okay. How's that look? Does it make sense? Okay, so we really haven't even done the example yet. That was just your notes. Example 1 has nothing to do with what we just did. Example 2 does. Now, the reason I'm giving you example 1 is because students instinctively right there want to divide by tan x. And you can't divide by tan x because sometimes tan x can equal 0. So if you divide by 0, that's not allowed. So to solve this, never divide. Oops, I guess we don't have to put never, never. You'll get the point if I just put never divide, okay? To simplify. Okay, so what we're going to do is we're going to minus tan x to both sides. That's allowed. So this would be tan squared x minus tan x equals 0. Okay, and look at our weird domain between 0 and negative 180. So we're doing this part of the graph, right? We're not even in there. So, factor out of tan. Tan x, that would leave me with tan x minus 1 equals 0. So then we're going, when does tan x equal 0? And when does tan x equal 1? So tan x equals 0 is here, where it's 1, 0. And here, negative 1, 0. So we're here and here. And this domain is in degrees, so we can answer in degrees. So remember, we are just dealing in here and here, so it happens at 0 and negative 180. Now instinctively, you'd want to say 0 and 180, right? Because most times that's the domain, 0 and 360. So this one, just mess with us a little bit. Two ways, we've got to make sure we don't divide, and let's keep an eye on the domain. The other one is, when does tan x equal negative 1? Now again, I don't get to play in here, so when does it equal negative 1? The only time is over here, because that is negative root 2 over 2, negative root 2 over 2. Or if you memorize your tans on your unit circle, that's when it equals 1 as well, sine over cos. So that happens at negative 135 degrees. So your answer is x equals 0, negative 180, and negative 135. And I did not put that in order, but you get the point, right? Okay, so let's do example, the new example with the steps that I gave you. Now, the negative 1 over root 3, that doesn't even look like something on the unit circle, but if I multiply by root 3 over root 3, this is negative root 3 over 3. And that should ring a bell. Okay, so the first thing we want to do is we want to solve for, when does tan theta equal negative root 3 over 3? Okay, and we're in radians. So cast, right? And it's happening here and here. And if it's happening there and there. So you can see this one. if you find this one and you add pi, you get the next one, right? That's happens in tan. But we could do this one as just like we would do a sine graph, right? Maybe we didn't recognize that these are 180 apart. Okay? Doesn't matter. You can do it just like we did the last question. So this is happening when? Are my answers? So at 5 pi over 6 and 11 pi over 6. Okay, that's when it's happening for tan theta. So 2, we're going to do tan 2 theta. So I'm going to do a horizontal stretch by a half. Now, first of all, how many answers will I have now? So I should have 4 solutions. So you go 1, 2, 3, 4. What would be the first solution? 5 pi over 12. How'd you get that? Multiply by a half. Okay? So remember, we're doing a horizontal stretch by 1/2. So when you squish it, you're going to get more solutions. That should make sense. And all your solutions should be half of what they were, or else how would I have got them in there? Okay? So if I take the first one and I multiply by 5 pi over 6, I would get 5 pi over 12 and 11 pi over 12. Now, to find the other two, we have to add the new period. Now, I can still go 2 pi over b, which is 2 pi over 2. So which equals pi. And in this case, I'm going to go, I'll just put AKA 12 pi over 12. Because I need a common denominator. So if I add 12 pi over 12 to this, well, because I've actually, if I wanted to, with this, I would just need the 1, and I could add pi over 2, pi over 2, pi over 2. But if I actually don't see that these two solutions are pi away from each other, I'll still pull it off. Okay, so, but if you say, well, it's tan, so I just need to find 1. And then I'm just going to add pi over 2 to every one of them. Okay, and that's 6 pi over 12. And do you see how these are all going to be 6 pi over 12 apart? Okay, I hope that's not messing with you, right? What I'm trying to tell Danny is that you can always do these with the over 2 pi. Okay, or you can just do, in fact, I would just recommend that for most of you. Okay, make it 2 pi over b, even when, so when you're doing multiple angles, it'll always work. Okay, but you can always check to double check. Make sure these are always your pi over b apart, all of these. Okay, so this would be 17 pi over 12 and 23 pi over 12. Does that make sense?
So you just do the first one just to see the solution.
Yeah, this helps me find the number of solutions in 2 pi, and then whatever this number is, I'm going to multiply that to the number of solutions. Okay, so this was 2 solutions. And this usually helps students if like sine x equals a half has 2 solutions, sine 5x equals a half would have 10 solutions. Okay, that's enough of an exaggeration of an example that students go, okay, so you just go 5 times, so I take this times this, and I will get that. Okay? Yeah, they could do 1/2, right? And then I would go 1/2 times 2. I should only get one solution. Because they've pulled it apart so far that it only happens once now in that domain. Yeah, if there's no solutions, that's a nice question. And I'm never that nice, so. Okay, we good? Okay, it's all yours.